muscle tissue in that it has fibers that have the same sarcomere pattern and myofibrils in them. They are different in that where the fibers overlap one another, they have these irregular areas that you can see in the image called intercalated discs, and within these intercalated discs they have two cellular junctions. Gap junctions, as you can see in the bottom figure, are just open channels with proteins called connexons that allow ions to go in between the cytosol of two adjacent cardiac muscle cells, and desmosomes tightly anchor the cytoskeletons together so that the cells stay together when the heart is contracting. So we're going to talk a little bit about the intrinsic stimulation of the heart. And what the intrinsic stimulation means is that the heart can beat by itself without any input from the nervous system. It does usually have input influencing it from the nervous system and other areas, but intrinsic just simply means that it does have the ability to generate its own action potentials and beat without the nervous system input, which is very unique and special. And the ability of the heart to have this intrinsic stimulation is due to 1% cardiac muscle cells being what we call autorhythmic or pacemaker cells. These autorhythmic or pacemaker cells can spontaneously depolarize, and then they can send that signal to the other 99% of cells, which also have many names. We may call them non-pacemaker cells, non-autorhythmic cells, or we may call them contractile cells. Another name or other names for the autorhythmic or pacemaker cells, you'll also sometimes hear them called nodal cells or non-contractile cells. So 99% of those cells are contractile. They cannot generate their own action potentials, but the special ability of the heart to intrinsically stimulate itself is due to those autorhythmic or pacemaker cells, which are just 1%. So those pacemaker cells are what we call self-excitable, and they can generate their own action potential, and we see a pattern of action potentials generating in those pacemaker cells in the image here. That green line is showing where there's a pacemaker potential showing action potentials in those cells over and over throughout a timed pattern. And they will communicate the ions that are generated in those pacemaker cells through the gap junctions to all those 99% contractile cells. So let's look a little bit about the electrophysiology of those pacemaker cells. So we are just looking at the 1% pacemaker cells, and what I have done is I have explained what's going on in the figure in the PowerPoint here, but I'm not going to read these. I'm going to look at the actual image and talk about it. So the pacemaker cell graph, if we're looking at an action potential and we're looking at the millivolts over time, so if we're looking at the voltage change in a pacemaker cell, the first step is that there is a slow initial depolarization. So what happens is the cell is hyperpolarized to begin with. And if we look at it here, it goes below its resting membrane potential here, maybe down to -70, and that is considered hyperpolarized. So that means it is more negative than it would be at its resting state. And hyperpolarization triggers the opening of a cation channel, and this is a non-specific cation channel. Pearson, the source of where this image came from, calls this non-specific cation channel an HCM channel. But notice that it's just letting positive ions in and out, and it's letting more positive ions in than out, so we notice a slow depolarization up to threshold at -40. And our threshold, if you remember that from the nervous system, is an all or nothing pattern. So there's a slow depolarization to threshold. Now, since threshold is an all or nothing, when we hit threshold, we completely reverse the membrane potential, and that means we hit full depolarization phase. -40 or threshold is the stimulus to open a voltage-gated calcium channel. The voltage that triggers the opening of this channel is -40, and when it opens, calcium goes down its concentration gradient into the cell and immediately reverses the membrane potential from -40 to +10, where it is fully depolarized. After it's fully depolarized, the cell must repolarize. This full depolarization to +10 will be the trigger that opens a potassium channel. Potassium, being a positively charged ion, will flow down its concentration gradient when potassium channels are open out of the cell. So potassium will leave And then potassium will continue to exit the cell and taking the cell past its resting membrane potential, and that will make it hyperpolarized. And if you remember where we started, hyperpolarization is what opens the non-specific cation channel, the HCN channel, and then we start over. So we get this same pattern where we see this pacemaker potential and the graph will look the same. Now these pacemaker cells that cause the intrinsic stimulation are always located in the same places in the heart. So we're going to identify those, and they are identified in this figure in yellow. The first area where we see these pacemaker cells are in the sinoatrial node, which is in the wall of the right atrium. Sometimes the sinoatrial node is abbreviated the SA node. The SA node cells will spontaneously depolarize about 90 to 100 times per minute, so this is the fastest times that these pacemaker cells will form that action potential. So for that reason, the sinoatrial node is normally considered the pacemaker of the heart because they spontaneously depolarize the fastest. So in 50 milliseconds, the signals from the sinoatrial node will travel through gap junctions to all the contractile cells in the left and right atrium. Then it will get down to another little bundle of pacemaker cells called the AV, or atrioventricular node. And these can spontaneously depolarize about 50 to 60 times per minute, something around there. But it's a little bit slower than the sinoatrial node. If the sinoatrial node were suppressed, then the atrioventricular node would take over as the pacemaker of the heart. The signals from there travel down this little bundle called the atrioventricular bundle. This is also known as the AV bundle or the bundle of His. Bundle of His is HIS. That's named after the Swiss cardiologist that discovered it. After it travels down the bundle of His, it can travel down the left bundle branches that you see are pacemaker cells that wrap around the muscle in the left ventricle, and the right bundle branch, which are pacemaker cells that wrap around the right ventricle. And then they're going to go into large diameter Purkinje fibers that penetrate deep into the ventricular muscle. All of those, since they are pacemaker cells, can spontaneously depolarize, but they can't do so quickly enough to generate a fast enough heartbeat to get oxygen to the brain. So if someone had their SA node and AV node suppressed, then they would need an artificial pacemaker. Now it takes 50 milliseconds after the SA node fires for the signal to travel through gap junctions to all of the atrial contractile cells, and it takes 50 milliseconds after the intrinsic stimulation of the bundle branches for the signals to travel through gap junctions to all the ventricular cells. There is a 100 millisecond delay here at the AV node and AV bundle before we go down into the ventricles. That's because the fibers are smaller diameter here, which is difficult to see on most figures, but functionally that 100 millisecond delay at the AV node is there so that the atria can depolarize and contract before the ventricles. So we see that information here. And an artificial pacemaker, if both the SA node and AV node were suppressed, would be on the left side, and it would be threaded through the clavicular area down through the superior vena cava, and you would have leads that go to the atria and the ventricle that could take over that spontaneous depolarization and set the rhythm of the heart.